In this video I'm going to talk about software, and I'm going to also provide a very brief introduction to programming and compare some popular programming languages. So software is made up of intangible elements of computing, unlike hardware, which is tangible. You can touch it, you can pick it up. Software is not like that. It's made up of computer programs and data. For example, Microsoft Word is a computer program which, when executed, emulates a smart typewriter. So a computer program is a logical set of instructions, quite precisely defined. At a high level, let's think about it as like a recipe for baking a cake. So you would simply read the instructions from the cookbook, and if they are accurately written, you should end up with a decent cake. Programming or software is written using a specific syntax, so that's a key word, syntax, in that it is the rules of the language. Spoken and written language have syntax. For example, in English we will start a sentence with a capital letter, end it with a full stop, and put words in the order of meaning. Programming is very similar to that. It's got its own rules, its own syntax, but break one syntax rule and your code probably won't run, whereas in a spoken language it's far more forgiving, because humans are more intelligent than computers, because computers are just not intelligent. We use logical sequences every day, so programming is just a way of automating sequences. Quite often we automate sequences that could quite easily be done without a computer, but the benefit of the computer is once we've written the sequence, it can be done very quickly and many times over, which I'll demonstrate later on. So let's think about a process or a set of logical instructions involving making a cup of tea. If you had to explain this to somebody who knew nothing about making tea, then what sort of things would you say to them? We can create an algorithm which is step-by-step set of instructions designed to perform a specific task or solve a particular problem, but it's programming language independent. So an algorithm does not imply any type of programming language. It's just a way of writing things down, a set of sequence of steps down succinctly. We could make it a little bit more program-like by using structured English in the form of pseudocode. That's something else that programmers sometimes use to try to get their thoughts down in a logical sequence, which then can be mapped to a particular programming language. But pseudocode itself is not. It is also language independent. You might decide that you prefer the visual approach and draw a diagram, such as a flow chart. So these are just steps to try to articulate the sequence of operations that you would eventually write as a computer program. So let's look at the visual approach first then. Making a cup of tea. Okay, basic steps. Fill the kettle with water. Alright, done. Switch it on. Obviously if you miss a step out, it's not going to work. If you fill the kettle with water and forget to switch it on, then this here, it's never going to exit, because we're saying, is the water boiling? No. Is the water boiling? No. Go back, have another look. If that step was missing above, this step here would never finish. So switch the kettle on, keep watching it until it's boiling. When it is, then you're ready to put the tea bag in the cup, add some water, and then here's another loop. This is another demonstration of a loop or iteration where we're going to repeat something, and we're going to repeat it a set number of times in this case. So we're going to say, how many times do you want your tea bag dunking? So you might say, well, for this particular person, they like it to be dunked 3 times. So we can set a variable to 3. A variable is just a named memory location where we can store a value, and then we can make reference to that value during the program execution. So we're going to say for this person they want 3 dunks, so we'll set it to 3. But in order to determine when we've reached 3, we need to count them. So we're going to have another variable here called dunks. Could have called it num dunks or number of dunks. Doesn't matter what you call it, as long as it's unique. Set that to 0. Okay, so now we're going to ask the question: is dunks, which is set to 0, less than max dunks, which is set to 3? That left hand pointer symbol is the mathematical symbol for less than. Well, 0 is less than 3, so that's a yes. So we're going to drop through and dunk the bag once. Then we're going to increment the number of dunks. So dunks was 0, it's now 1. And we come back round and we're going to do the comparison again. Is 1 less than 3? Yes, it is. So we're going to dunk it again. Increment the dunks counter, come round again. It's now 2. Is 2 less than 3? It is, yeah. Give another dunk. Now it equals 3. Is 3 less than 3? No, it's not. So I'm going to follow this route instead. Do you want to add milk? Yes or no? This is effectively asking the question: if you want milk, add milk, else don't add milk. Here's another if type scenario: if you want sugar, add sugar. If you don't add it. Absurdity is another if type statement. If you want another cup, we'll go back to the start. If you don't, else, finish. So that quite neatly describes the sequence of operations that could then be implemented in a computer program, which might be the computer program in a vending machine. So let's look at the software types then. But application software. Application software is a sort of an umbrella term which you'll see incorporates most applications. So application software is designed to run on computers, perform a task for the user. And we have desktop applications, for example, such as Microsoft Word. It runs on your desktop, in your laptop or whatever. Teams, PowerPoint, computer games. So we tend to refer to them as desktop applications, so that they're a member of the application software group. Web software is also application software, but it tends to be associated with the internet. So we typically have a client, which is an application running on your machine within a web browser, like Chrome or Edge or whatever. And there's usually a program running in the back end as well, which is somewhere probably on the cloud. So there's 2 programs usually in these web solutions, and we'll get onto that in a future session. So a website, for example, online banking, online shopping. And as I said here, you normally have a front end on the desktop, which is the user interface. That's where the user is able to provide instructions to the back end, which then the front end and back end was discussed in a previous video during the infrastructure video on hardware, and also discussed on the one about networking. And then the back end runs on a server, and they're both connected via the internet, typically. A disclaimer about all this stuff is that obviously this is a very high level discussion, and so therefore I'll be using quite a lot of technical license, and so I'll be generalizing a lot, and so obviously there are exceptions to most of the things that I'm saying, and there's also a lot more detail behind everything that I'm saying. Okay, mobile apps, another subset of application software designed to run on a phone. And this is, again, it uses programming, but it tends to use different programming languages than we do for desktops. But you've got things like online banking, shopping, Facebook, etc. But you've got them on your phone. System software. This is a different category. So all this stuff here can be badged under the umbrella of application software. System software is basically operating system. So the operating system, which I'll talk about shortly, manages and supports the computer hardware and system operation. So it's not really something you tend to, or the average user tends to use very much. It just runs in the background and does some sort of like back office type functionality. But I'll discuss operating system shortly. Typical operating systems are Windows, which is very popular for desktop and web front end. For well, most desktop devices. There's Mac OS for people who like MacBooks, a different operating system, and there's Linux. Can be used for a front end, but in enterprises tends to be used at the back end. But either way, these are the main different flavors of operating system, and Linux comes in multiple flavors. There's things like Red Hat Linux, CentOS, Ubuntu, various distributions of Linux, but fundamentally at the core they're all the same. Okay, so where does software live? So software is stored in a file on disk. So it's stored on a disk somewhere, and we need to be able to load that file from the disk into RAM. So to execute it, we're going to need to convert the source code, which is on the disk, or you'll see in a minute when I explain it, it could be the executable code on the disk, but for the moment we're going to take a file, ensure that it's in the correct format for the microprocessor to understand, load it into RAM, and then from here the CPU will read the code from here and execute it. So the CPU is the execution engine. It will go and find the start of the program in here and execute the instructions that you've written. How it gets from the disk into RAM and the processor kicks off the execution is all managed by the operating system. Alright, let's look at a simple use case. Let's look at this. So we're going to design this and then write the solution in a programming language. In fact, let's use a few programming languages. So we'll generate a times table of a specified multiplier, which is a table value, and an incrementing multiplicand. In other words, we're going to output 1 times 5 is 5, 2 times 5 is 10, or it could be whatever we want to go up to. It could be 12. It could be 200. And the table could be 5 times table, 10 times table, whatever we want. Just it's programmable. Okay. So I'll do it in 5 different languages and we can compare how similar or not similar they are. So here's the basic flow chart. We'll set a table value. So we want the, in this case, 5 times table. We'll set a maximum count. So how many of them want? Let's say we have 12. That's quite typical. Okay, so we'll set the counter so we can count how many of these things we've output, because we want to output 12 in this case. So we want to set the counter to 1 and let it go up to 12. And so we're going to have a loop like we did with the teabag example. So is count, which is starting at 1 in this case, less than or equal to max count? And max count is we'll set to 12 in this case, but it can be set to whatever you want. Is 1 less than 12? Yes. Okay. Output count times table. Count is 1 times the table 5. 1 times 5 is 5. So it's going to output that. Then we're going to increment the counter, just like in the teabag scenario. increment the counter. Count is now 2. Is 2 less than 12? Yes, it is. And you can see it's going to keep going around here 12 times. So eventually these two, that count is actually greater than max count, and we will drop out and finish. Okay. So let's look at it in terms of algorithms and pseudocode, and then we'll write some actual code. Alright, so as an algorithm, algorithms are fairly generic in nature. And so this is going to say multiply each number from A, which is a number, to B, which is a number, so this could be 1 to 12, by C, which could be the 5 times table. In other words, the algorithm is saying generically, we can take one number as a start range, second number as the end range, and then multiply by a third number, which is the table, and display each result. So that's it, quite succinctly written. You might want to now move from that to something that's more program-like, but not any particular programming language, so that, for example, one person could write the pseudocode like this, and then you could pass it on to multiple programmers who may, for some reason, want to write the solution in different languages. One programmer might be writing the solution for a desktop application, another one might want to write the same solution but for a phone, so they're using different programming languages, but they can use the same pseudocode. So this is going to just explain what the programmer needs to do. So we're going to set table to 5, so that's set table value, as we see in the diagram, if that's the way you wanted to document it. Set max count to 12, so here's the set max count, we'll set it to 12, and set the count to 1, initialize that to 1, because that's going to be our counter starting from 1. Then we're going to describe the iterative loop, this one here. Repeat while count is less than or equal to max count. Alright, so we're going to, these two lines here are going to be repeated until count is greater than max count. Show, as in output, I could have written output, count, which is the counter, so it's going to be 1 to 12, then a cross to indicate times, table, which is set to 5, equals, and then we're going to actually multiply the two together and output the result. Then we're going to increase count by 1 and repeat again, keep going until count is greater than max count. Alright, so that's just an English written version of this diagram. It's a lot easier to write that than it is to spend time drawing that diagram, as I know, given that I drew the diagram and I've written that, and this is much quicker. Now let's not write it in a particular programming language. So you can see this is it's only one step removed from the pseudocode to the programming language. This is JavaScript, and was just saying that table equals 5, similar to that. Well, this is written specifically in the language. It's got to follow the syntax rules, otherwise it won't work. Max count is 12, so there we are. I've set these as const because during this program execution these two values won't change. And then we've got this for loop. This is indicating a loop. Now, I'm not going to discuss this now because I'm going to give a demo of this, but basically this is going to implement this loop here. It's going to execute this statement here whilst count is less than or equal to max count, but I'll go through that step by step in a second. Now, we can't run this, the CPU can't execute this code because it doesn't understand it. It's a foreign language to it. This is English readable or human readable, whereas a CPU works in binary. It wants the code to be written in binary. So we need somehow to convert this human readable code into something more like this. So this human readable source code needs to be converted into machine code, the code that the machine can understand, which is binary numbers. So I'll discuss that Now, there's two main ways of doing this to convert from the source code into the machine code so that we can execute the code. One is using an interpreter. An interpreter is itself a piece of software that runs on your computer, it needs to be installed, and it converts source code into machine code. So if we've got JavaScript, we need a JavaScript interpreter to convert JavaScript into machine code. If we're using a Python, we need a Python interpreter to convert Python into machine code, a bit like a translator translates English into French or whatever. Okay, the key thing about an interpreter is that one line of code is converted to machine code and then it's immediately executed. Then the next line is converted to machine code and that line is executed. So the benefit of that is mainly that you can quickly test code as you write it, add another line, run the program, then you can even execute it one line at a time. And it runs on any system where the interpreter is installed, as long as you've got the right interpreter, because, for example, an x86, say Intel x86 series microprocessor does not follow or does not understand the same machine code as an Apple Mac RISC based processor. So we need to make sure that our source code, or human readable source code, is converted to the correct machine code. So in other words, you need to install the correct interpreter. The downside of using an interpreter is generally slower to execute than compiled language. In examples of interpreted code, it's Python. Python is an interpreted language. JavaScript is PHP, popular for websites. Ruby and Basic, not used very much anymore, but it's interpreted. A key downside of this is that when you distribute your solution, then you need to distribute the source code, because the interpreter needs to read the source code to generate the machine code to execute. So it means that your original human readable code needs to be distributed, and so that means that, you know, if you sell your program, then anybody who buys it can read the code, they can modify it and then pass it on as their own, because they've got access to all the original code. The alternative is to use a compiler. A compiler translates the whole program into machine code and saves that machine code in a file, and so this is executed not a line at a time, but the operating system will load the executable file, the whole file, into RAM and then execute it. This tends to execute much faster, which is a plus. You deploy your code, you deploy the machine code version of your file, so it's just binary numbers, so it's very difficult for somebody to copy your code or even understand it at all, because it's just a lot of binary numbers. I'm not saying it's impossible, but it's very difficult. And so you would tend to distribute an executable file. So for example, if you looked in your file system, you'll find, if you've got Word installed, you'll find a file called word.exe, and that's an executable file. It's just full of binary numbers, and so you keep the source code to yourself, the readable stuff. You don't deploy that. I've written here something I said earlier, that is that machine code will only execute on the machine that understands that particular code, so you need to make sure you've got the correct compiler, in a similar way that you need a correct interpreter for your type of machine. So in other words, there's no point in having a compiler or an interpreter that generates RISC-based machine code for an Apple Mac when you're running on a Windows-based x86 machine. Examples of compiled languages tend to be the more powerful languages, such as C, C++, Java and Rust. And I'll demonstrate the more popular ones. Rust is quite new. So how do we write this code? Well, you can just write it in a normal text editor like Notepad or something, but that'll make life quite difficult for you. So we tend to use these integrated development environments, which is a tool, again another program. It's a tool that helps you to write the code, debug and test the code all in one place. There's a few popular ones. I'll just whiz through some of the more popular ones. Visual Studio Code, which is the one that I'll be using to demonstrate in a minute. It supports many different programming languages. It's a general purpose, lightweight, easy to use, free from Microsoft, very popular for JavaScript. But other languages are available. I'm going to use it today for all 5 languages. PyCharm. This is a full-featured development environment for Python from JetBrains. There's a free community edition if you want to use that, or you can pay for the professional version. Eclipse was very popular, perhaps not quite so much now, mainly for Java development. Again, that's free. IntelliJ, another product from JetBrains, mainly for Java. Well, it is for Java. And then NetBeans, again, was written mainly for Java. That's free. Visual Studio, I'll put this in. It's not the same as Visual Studio Code. Visual Studio Code is very much more lightweight, easier to use. Visual Studio is a full-blown, highly complex, integrated development environment. It supports multiple languages. It's mainly for creating .NET type solutions. Don't worry about what they are, but you would tend to use it for writing programs in C, C++, C#, and it's also good for enterprise type web applications. It's heavy duty in comparison to its lightweight Visual Studio Code. There is a free community edition, or you can pay for the full enterprise version. Okay, so what I'll do now is I'll do a quick demonstration of some programs. That's what this red thing is to remind me of. So I'll do this demonstration in using Visual Studio Code. So this is a demo of how an IDE, an integrated development environment. It looks a bit intimidating at first, but it's actually really easy to use compared to some. And what we can do is it's a text editor, so you can just write your code in here. I've written some code already, so I can look at the files that I've got here. So here's the different programs that I've written. So let's have a look at the first one. So I'll look at the JavaScript times tables, the one that was in the slide previously. So I said before that the IDE allows us to write the code, which it does. I mean, just type this stuff in. Here you can just type in whatever you want. Debug the code. That means we can fault find if it's not working properly, and test it. So this code is very simple. It works. I could probably try and break it in a second to look at the debugging, but I'll just run it to start off with, just to be able to test this and see some output. We can just provide an output window down here, this debug window. And so when I run this program, don't forget JavaScript is an interpreted language, so I can just run this. We can just go run, and there it is, it's output what we wanted, 1 times 5, 10, 15, 20, whatever. And the benefits are obviously not, it's easy to do by hand, but once you've got a program, you can very easily go change this to a 50 times table. Well, let's make it more difficult, a 51 times table, and we'll have 120 iterations of it. Now to do that by hand would be pretty difficult. Well, it's very time consuming at least. But here, just run it again, and that's it. It's just going to output all that as quickly as that. We could even decide we're going to have start from negative values. Let's say we're going to start from -12. Well, we'll start from -12 and go to +12, so we can say count is I don't know why I bothered doing this really, but you see you can go from -12, -11, -10 through to 0 and then through positive. What I'm trying to point out here is that it's very flexible. So count is just a start point, and typically you'll start at 1 for a times table program. Alright, now say this wasn't working properly. I can't think, because it's so simple I can't think of how to break it. Let's say instead of using this star, which is a multiply symbol, let's say we use plus instead. We got confused, and we run the program, and you think, oh crikey, that's not right, that's not coming out with the results I expected. So we need to try and debug this and find out what's going on. Now to show you the loop, what I'll do is I'll just show the side by side briefly with the original flow chart. So there's the flow chart we're trying to implement, and here is the program that's implementing it. But the IDE allows us to debug the program. Now in JavaScript and most languages the layout is fairly flexible. You can put these things on statements on different lines, etc. So we would normally write a for loop like this in one line, but to be able to show you the different elements of it, just to get the point across about how this loop thing works, then what we're going to do is we're going to say for, which is implementing this. Starting at count is 1, keep going until we get beyond max count, and every time you go around the loop increment the counter. So plus plus means add 1. So count is 1. When you execute count plus plus it goes to 2. If you execute it again it goes from 2 to 3. And we will execute everything inside these braces, and if you wanted to you could put the braces down there to separate it out. The layout is quite fluid, but I'm doing it this way so I can show you how the debugger works. So in here I can put breakpoints, these little red dots, and I can make the program step one line at a time. So I'll put some more in down here, and we can see it bit by bit. So if I run this program now, the menu's been, I'll press a shortcut key just to run this in debug mode. Alright, so here we are, it's stopped, and it's showing us that we're going to assign 5 to table, so we can check that. Now if we look at table, nothing's been assigned yet, that's just telling us what's been written, because this yellow arrow is showing us the line that's about to be executed. If I press this button here, it'll execute that one line. Okay, so it's done it, it's moved to the next one, and table should now equal 5. Similarly with max count, when I execute that, max count should equal 12. I can roll over that and I can see it's got 12 in it. So this is really useful. So let's see how this loop works then. So this initialization statement. This only gets executed once. This is just to start the loop counter off. So I'm using let this time instead of const in this language. This means I'm creating a variable that will change, or is allowed to change, because we're going to have counts going to go from 1, and it's going to increment to 2, then 3, then it's going to go to 12. So that's going to execute once. You can see it's going to do it here. So at the moment, count has got nothing in it. Execute it. It's now got 1 in it. So we've done this here, set count equal to 1. This only happens once in this particular construct in this language. Then it's going to say is count, which is 1, less than or equal to max counts, which is 12. Well, of course it is. Now the only unintuitive bit here is it's going to jump over this next statement, execute all statements in between these braces. If there was 100 statements in here, it would execute all of them, and then it will come back and increment the counter for us. In other words, it's going to increment the counter afterwards, like it does on this flow chart. Alright, so increment, I'll execute that. So you see it's jumped from there to here to do the execution, exactly like it does here. It's done the test. Is one less than the other? Yes, it is. So it's now going to execute that command there. This is going to output. Now it looks a bit complicated because some things are inside curly brackets with a little dollar symbol. All this is saying is that if it's inside these curly brackets, then don't output the word count. Output the value of count, in this case which is 1. Because this x is not inside the brackets, it will output x. This one is not going to output 7, it's going to output 5. Here though, it's not in brackets, so it's going to output equals. And then here it's going to output the value within the brackets, so it's going to get count and add it to the table and output 6 at that point. Okay, so when I execute that, we should see 1 times 5 equals 6. And immediately you can see, there's something not right there. 1 times 5 is 6. And you can start looking at your code and think, oh, look at this. Obviously that's not right, is it? That should be 1. That should be count times 1 times 5. Alright, now we've fixed that. We can just restart with this little green thing. Give it another go. And we can step through again. And you can see it's going there. Execute the code. 1 times 5 is 5, so that looks okay, but it might only work for the first one. Let's just check it out. And a breakpoint on there as well. So it's come back. We missed the increment there because I didn't have the breakpoint on, but just execute the next one. We'll see that once it's done the execution, it's going to increment count like it does in this diagram. So it's going to output the next one, 2 times 5, and then you can see it's jumped up here. Count plus plus, so it's incremented count. It will increment. The count is 2, it's going to increment it to 3. When you execute it, execute that, count should now be 3, which it is. It's going to do the comparison. Is count less than or equal to 12? Yes, it is. So execute this block again. So you can see you can step through one line at a time, one statement at a time, and you can, this way it can help you to debug the logic of your program. So that's another benefit of using an IDE or an integrated development environment. I'll take these off now. So I've got one there, and okay. Now we wouldn't normally write it like that. I've only put this on separate lines so that we can see the debugger doing a line at a time. But if you wanted to write it like that, then it's entirely up to you. You've got the freedom to do that. You'll find when we look at Python, you've absolutely got no freedom to do anything like this. Okay. So we don't need this anymore. I'll make this a bit bigger. Clear that. Right, so let's look at another language now. What I'll do is I'll look at C. Now C is a compiled language, and I'll put it in side by side. So I'll put it over here. So I'll open this C program, or is it tables.c over here, and we can compare these two. Oh, actually, I've still got this written in this strange way. Let's put this back to how it was. Okay, so you can see that these two languages are very similar. Alright, we've got an extra line here, and it's slightly different in how we assign the variables, but not much different. We've got table equals 5, so it's table equals 5 there. Max count equals 12, that's the same. We've got this little bit here, where this is the main program that runs everything between these two yellow brackets. We don't have that in JavaScript. But look at the actual body, the main bit here. It's more or less the same. Count equals 1. Here we got count equals 1. Or counts less than max count, count plus plus, well counts less than max count, that's the same. The difference in this particular example is really only the output. In this case it's console.log, and we're still outputting count times table, and then outputting the products of count and table. It's just that the syntax is a little bit different. Here I'm using printf, and I'm still outputting count and table and count times table. So I'm doing the same thing. And you might think, oh, well, these curly brackets would look a bit different. Well, that's no problem. We can make that the same. We can put that up there, like this one, and the matching one down there. And the IDE helps you with that, because if you click on that, it shows the matching brace. And so this is a block. So everything within this block, in other words, just this one statement at line 6. But if there was 20 statements in here, they would all be executed as part of the iterative group, because they're inside the brackets, which indicates a block of code that's going to be executed multiple times. There's not a lot of difference there. One difference is this is a compile language. We need a compiler to run this. I can't just press run on this one. I need to create the machine code and run the machine code. Okay, so I'll do that here. We can go to the terminal, or the command line, it's often called. I need to run the compiler, so I need to install a compiler, and I think I've installed GCC. So I want to compile, CC being the C compiler, I want to compile tables.c. Now if we look at the files I've got here, tables.c is there. There is no tables.exe. I'm going to create that now, the machine code version of that source code. So GCC, tables.c, and I want to output, so -o, tables.exe. So I want to create an executable file, in other words, a file with machine code in it. So if I do that, then we see tables.exe has been created. If I look at that, the IDE is saying, do you really want to open this? It looks like it's a binary file, because it is. It's a binary file. It's got machine code in it. So that's exactly what we wanted. The CPU will want the code to be written in its own machine code, its own language. But we can look at what that looks like just to show you. So tables.exe, I want to open it in the IDE. I'll open it with a viewer, and this is what the machine code looks like. So this which is human readable, has been converted into this. Now you might say, hang on a minute, that's not binary. But what it is this is hexadecimal. Now I know that you might think, oh, you've not even discussed hexadecimal. No, I haven't, because this is a high level discussion. But this is just a more succinct way of writing binary numbers. So for example, I know because hexadecimal is easy to convert to binary and binary to hexadecimal, and hexadecimal takes up much less room because each digit in this hexadecimal code is 4 bits. So that B is 4 bits and that A is another 4 bits. So I know, for example, that this one here in binary is a nice easy one. It's 0 0 0 1 1 1 1 1. Now I can confirm that if I just click on that. You can see it's got it. It shows the binary value here, 0 0 0 1 1 1 1 1. And you know they're all fairly easily convertible. This one here, for example, I mean CD. This is going to be 1 1 0 0 and then 1 1 0 1 1 1 0 0 1 1 0 1. So this is binary underneath. It's just, this is just making life a bit easier for us by displaying it in a smaller set of numbers. Otherwise we'd have 8 numbers for every one of these digit pairs. Okay, so basically this is what we're going to distribute. So when you sell your program, this is what somebody gets, and so they go, well, you know, you can't make head and tail of that. I'm not going to be able to easily rip this off. All right, so that's C. Now because I've got an executable file, tables.exe, I can execute that file. So I can just say tables.exe. Now it's a bit slow, probably because it's kicked off my antivirus that's checking the file. Okay, it's done it now, and the antivirus is saying good news, this file looks safe. Well, thanks very much for that. So what I'll do is I'll run it again to show it's not that slow. C is the fastest of all of them. And make a bit more room and you can see a bit better. So if I run that again, it's sort of, you know, it's immediate. Okay, let's have a look at a different language then and compare it to this. So C++, I'll do that in a separate window as well so we can do the comparison. CPP, so it ends in CPP, this is C++. C++ is based on C. C++ adds object-oriented functionality to C. I'm not going to talk about what object orientation is, but other than say that it does. But look at them; they're pretty much the same. Alright, the include is including a different file, but this line is the same. This is the same. Everything's the same, apart from again the output, how the data is output. Now because C++ is built on C, I could have used this, and that would still have worked. But this is more of a C++ way of outputting stuff. But you can see the languages are pretty similar, and this is a compiled language as well. So just a note, to compile this into machine code, even though it's very similar to this, I'd need a different compiler. I'd need a C++ compiler. So I'll go to C++ compiler. So let's clear this, and you can see what's going on. So which one have I used? Oops. Tables, what do I call this? Tables.cpp, tables.cpp, and I'll output, I'll call it tables2.exe, otherwise it'll overwrite the other one I've got, which is called tables.exe. And I don't know what you're thinking, I'm cheating and using the same file as last time. So if this runs, okay, we should now have a tables2.exe in our list. Tables 2. So I should be able to run that one. So I can put it in .exe, I will do. But in Windows it will assume exe. Oops, no switch file. Tables, what have I called it? Tables2. Oh, I've missed a dot off. Fat finger syndrome. Tables2.exe. Alright, thank you. Antivirus, yes, that's that file's clean. To demonstrate that that is the C++ one running, I could just as easily change this like I did previous to the ones. But of course, unlike the JavaScript, I can't just run that, so I'm going to have to recompile it. So I'd need to update the output file there by recompiling it, and then I'll need to run it again. Yep, thank you. Antivirus says that one's okay. And so we see, just like that, not rocket science. Alright, what else have we got? So that's C and C++, very similar because they're very closely related languages. And again, the formatting here, you would probably quite typically put the brackets up like this, just to show the layout is fluid. You can do what you want in these proper languages. Let's have a look at Java. So I'll open Java in this side and compare Java with the C++. Where is it? Let's get rid of that one. Tables dot. Oh no, that's the one I wanted. Tables dot Java. There it is. Right. Let's compare these two. Let's clear this line off down here. Alright, so now C++ supports object-oriented programming. You don't have to, it's optional. You can write the code in object-oriented fashion, of which we've not discussed, or you don't have to. It's very flexible. You can just write C programs in here and it'll still work. With Java, it's only object-oriented. You've got to write it in an object-oriented form. You don't have the flexibility you have in C++. And so we have to have this public class tables thing at the top, and other stuff that you need to put in when you're creating object-oriented solutions. So we've got public, static, void, main. So this is sort of the equivalent of this main here. We got a bit of extra guff around it because it's creating this thing called a class. But when you get in amongst it, it's very similar. Table equals, oh, I've got 50 there. Let's say table's 5 and max count is 12. Table is 5, max count is 12. This is the same, I've only just put on different lines. And the for loop, exactly the same. Count equals 1. Count's less than max count, that's equal to count plus plus. Now again, the difference is the output. It's just a different syntax for outputting stuff, but very similar. It's still outputting count times table equals count times table. Right, so it's just different syntax, more or less, almost just for the sake of it. I don't get it. But anyway, this is a compilable language as well. Java is compilable, so we need a Java compiler. So I've got a Java compiler, Java Java compiler, and then the name of the file I want to compile is this one, tables.java. Java. Okay, and okay, that's created. That should have created a file called java.class. Sorry, tables.class. There, I can execute that. So, to execute that, then I'm just going to what happens with pressing buttons on the keyboard and they don't do anything. Okay, tables.class. Not fine, I'll load main class tables.class. Okay. Tables.class. Couldn't find it. Oh, I think we don't need to specify the class. I think it's just looking for the name of the file. These are just the foibles of different languages. So there's the Java being executed, and again you can do whatever you want. Let's say 15 this time, and 112. Need to recompile it. So Java, there's Java compiler, the file is tables.java, and then we can execute it. And then we've got up to 112 by 15. Java looks very similar to C++, which looks very similar to C, which looks very similar to JavaScript. The syntax is very similar. For loops are the same. Many other things are the same. ++ means increment in all of them. Let's have a look at Python. Tables.py. Right, this looks different. Python apparently has been written for beginner programmers, and so the syntax has supposedly been simplified. Now, I'm not convinced by that, but then again, maybe because I'm coming from a background of writing these type of languages, maybe I'm being a bit biased, but I find this syntax more awkward. But anyway, let's just go through it and see. So it's an interpreted language, and so we don't have this include stuff and various other things, but we've got table is 5, the same, max count is 12, is the same. This for loop's a bit weird to me. I think the idea is that the Python developers thought that ++ to increment a counter was too complicated for people to understand, and so they've changed the syntax of the for loop, and they're now saying for count in the range from 1 to max count, but max count is actually 1 less than what we want it to be, so we need to add 1 onto it, and then you need to stick a colon on the end to say this is the stuff underneath here that we want to execute. When you do that, then the print, again, the output command is different than the others, but very similar. We've got the actual values we want to output in curly brackets again. Other than that, it's just slightly different. So you can see that if you can learn one programming language, transferring to another is not so difficult, especially if you've learnt one of these types of languages, because the syntax is very similar in both. Maybe moving from Python to one of these other languages might be a bit more steeper learning curve, because the syntax is different. And I'll show in a minute that unlike these other languages where you can literally free format the code to look at however you want it to look, you've got to be very careful about how you lay out Python code. So because Python is an interpreted language, I should be able to, I can run it without having to compile it. So let's just clear this up a bit. And I should in theory in Visual Studio Code be able to run this in debug mode. Okay, so there's the Python output. Right, now let's just compare. I mean, that's it really. It does the same thing, but it does look different. Let's just compare that with the JavaScript, because that's interpreted as well. So I'll find the tables.js, where it is, tables.js. In fact, I'll open that in the other window, then we can compare them, tables.js. So I'll have them side by side, and here's the Python on this side. I'll make a bit of room by closing that bit. Right, so let's have a look at how these compare. So if I want to, I can add another line in here, and I'll output something else. Output I'll just output something for the sake of it. Now what this is showing is that inside the yellow brackets there's a block. It's clearly saying that we want to output both of these statements 12 times. Okay, so if I run that, there's no ambiguity about that, so I'll just run that. So you can see 1 times 5 is 5, then output just for the sake of it, and then 2 times 5 is 10, then output just for the sake of it. It's putting them both out. I could put that one there if I wanted to, and it will still run. I could put this one here and it'll still run. I can put the bracket down here. Oops. And it will still run, because it's very clear that the for loop is executing everything inside these brackets. Now the people who wrote Python, I just put seem to think these brackets were complicated, and so they've taken them out. And the problem with taking them out is there's no way of easily indicating a block. So say for example I wanted to print F. You see, now because if you've got a decent IDE, it's telling you, oh, this is Python, and you're not allowed to do that. This probably won't run. So I'll try and execute it. Okay, so it didn't like that. Execution error occurred. Okay, printf is not oh, because that's my fault. That's the C version, and this is the irritating thing about the different languages. They're different, but only by a bit. So printf is C, print is Python. So if I run this, you think, okay, I'm going to run everything in this for loop. And so you run this in the same, expect the same output as last time, but oh, hang on a minute, it's not done the same thing. It's written all the timetables out correctly, but it's only output just for the sake of it once. That's because in Python you've got to line these things up, because you don't have curly brackets to try and make things simpler. You've got to align things in blocks, and so to get both of those to output, we have to indent them both. But you can see the IDE is saying, oh, I don't like this here, because it's thinking, is that meant to be lined up with this one? Because the alignment is important. To output both of these statements, they've both got to align with each other. So if I indented that by 1, I'd have to indent that one by 1 as well. And then it should run, and its output each one correctly this time. So you need to be really careful with Python in that the number of spaces has to align. So you need a good IDE that's going to show you the alignments and give you errors if they're not aligned properly. Now I think that is more difficult than just simply putting brackets round whatever you want and then just saying execute all that lot in between those. But anyway, you know, that's only my personal opinion. Okay, so there's a comparison of 5 different languages. I've looked at some that are interpreted, which I'm going to just run straight away without compiling, just like these two have, and some need to be compiled. So let's look at the difference in performance between these languages. So let's say it's a bit of a tidy up here. Let's just look at a simple speed test. Now let's look at C. So what I'll do here is I've got a for loop, you know how that works now. It's just going to continually execute whatever is inside the curly brackets. Well, there are no curly brackets, so it's going to execute nothing. So what it's going to do is it's going to set this variable to 0, and then it's going to check if it's less than 1 billion. And if it is, it's going to increment, and then check if it's less than 1 billion, and if it is, it's going to increment. In other words, it's just going to count from 0 to 1 billion minus 1. And what I'm going to output is just the final value, which will be 1 billion. Okay, then it's a printf is going to output it. So in other words, I'm just going to see how long it takes for this program to count from 0, well, to count 1 billion iterations. Now this is in C, so I'm going to have to compile it. So is it BCC or GCC? I think I'm using G. What do I call it? Speed .c. I'll output it as .xc. Okay, so I can execute that now with. I don't need to put the .exe on in Windows, it'll recognize it. Well, it should recognize that. Now, that seemed to take a long time, probably several seconds, but that's because the antivirus kicked in again. So what I'll do is I'll run it again to give it the proper speed. So I'll run this and then count how many seconds it takes to count to 1 billion. So I'm going to press it. Now, well, I didn't even get. It wasn't even 1 second. All right, so you know you can't get anywhere near 2. I press it now. 1. Right, so it counted to 1 billion and an output there. If I did some similar things with Java and C++, they're going to be pretty much just as fast. Let's try the Java one. So speed.java probably. Just to look at it, speed.java, just the same, can count to 1 billion, it's going to output the result. So if I compile that, I get this speed.class there. So right, again, it's basically instantaneous. Ready, press it now. Boom. If anything, it seemed even quicker than the C one. So these compiled languages are very fast. Let's have a look at the Python one. Python speed dot pi, there it is. Alright, so 1, 2, 3, 4, 5, 6, 7, 8, there's 8 notes there. The reason I put 8 notes on instead of 9 like the others is because it's going to take too long. So I'm going to get it count up to a tenth of a billion or 100 million so instead of 1,000 million, and then output the result. So I'm not running it in the debugger so that I'm going to get the maximum speed out of it, so I'll run it Python speed py. So I'm going to press it now. 1, 2, 3, 4, 5, 6. Right, about 6 seconds. And so if I'd have put the other 0 on, like I did with the others, we'd have been sat here for a minute waiting for that to execute. Now that is massively slower. Now I know that you know, people, if anybody watches this that knows about programming, they say, well, hang on a minute, we can speed that up. Well, you can, but this is supposed to be the beginner language, and so that's how you would write it. If you wanted to use Python in a more professional setting, then yes, okay, you can link in some high-speed libraries. I'm not knocking Python completely, I just don't like the syntax. You can include libraries of files that have been written in other languages, so we can execute code from within Python using the Python syntax, but execute blocks of code that have been written in other languages such as C. So we can make Python very fast by effectively not making it Python anymore, in a way. But again, that's my probably biased opinion, because my background has been in C and C++. So there we are. Interestingly, Python is interpreted, so you think, oh, okay, interpreted programs are really bad at performance. But let's have a look at this JavaScript. Speed.js. Here's the same program. Again, it counts up to a billion. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros there. I'm going to leave all 9 zeros in here. And I'm going to run this in what you would normally consider to be a back-end environment called Node.js. So I'm going to run this as a Node.js application. So, but it's still JavaScript. So Node.js. I forgot to count, but let's count it. Go. 1, 2. All right, 2.5 seconds or something like that. Certainly slower than the C, C++, and Java, but nothing like the Python in its standard syntax format like that. Okay, people who love Python will be saying, oh, that's not a fair test. But, you know, I've written a for loop that counts to 1 million. I've written a for loop that counts to 1 million. And, you know, it's an example of how you can run into performance issues if you don't know what you're doing, or if you don't know more advanced programming techniques. Okay, that is the demos of programming, the introduction to programming, or an overview of programming. To go back to the slide deck just to finish off, the last part I want to talk about is the operating system. What does it do at a very high level? Okay, so operating systems such as Windows, Mac OS and Linux that I mentioned earlier, they can be used for desktop applications, and they can be used for back-end processing as well. And if you're only watching this video and not watched the previous ones, then you might not know what I mean by back end. So I suggest you look at the previous videos on hardware and networking. So this is software that coordinates access to hardware for your applications. So in a very high level view, here we've got various software running on the computer. I've called it user apps, and these will be executed in RAM. Here we've got hardware, we've got the screen, the keyboard, printer, disk, etc. Lots of other hardware. And the operating system sits in the middle. So, for example, when you start Word, say we found the word.exe. Well, I can show you that. Here it is in program files, Office, Roots, Office 16. This is where it is on my computer. If I sort these into application type and just scroll down, we can find the executables. So what we got here then? Excel, excel.exe. You can see there's the machine code version of Excel. Other things that I'm familiar with: Access, Microsoft Access Database, executable. Microsoft Publisher, mspub.exe. So these are the these have been written in probably in C or C++, and then compiled into executables. And so these are the files that are distributed. There's OneNote and PowerPoint.exe, and then Visio.exe, and there'll be Word down here somewhere, WinWord.exe. So these are executable files. We can even look at them if so I can just show you that there's nothing different about these, because they're professional programs, than let's look at Word. So as I was saying before, it's just machine code. That's what it looks like. These are the binary numbers that are associated with it. But if I launch it, if I execute it, the operating system will load this machine code into RAM, and then the CPU will start executing the code that's in there. So if you double click the executable, then I can see Word is starting up, and there it is. Okay. So when you open Word and you start typing your great piece of documentation, then what's really happening is you press a key on the keyboard. The keyboard is hardware. The hardware will generate a number, a binary number associated with the letter that you've pressed. That will then pass that to the operating system and say, I've got a letter W, and I want you to send it to word.exe. So word.exe being one of the Office applications, the operating system will pass that W to here, and so it's going to write that, not just on the screen, but it's going to write it into RAM at a specific point, and the contents of the screen that you see are actually being written to the hardware screen. In other words, there's a graphics card within the computer, and so the operating system writes what Office looks like into the graphics card, which is then displayed on the screen. And you press a W, it's going to update the picture, because that's all you're seeing on the screen when you're looking at Word. It's just a picture, and it's going to update the picture and put a W in it, and then you'll see the W appear on the screen. When you save the document, you say, I want to save what I can see here. And what's going to happen there is a file save. that's Office or Word is going to send a request to the operating system saying I want to save the contents of this file. In other words, the data that's in RAM associated with this file, I want you to go to RAM, find that data and copy it onto a disk using a file name that I've just provided. So it'll write it to the disk. You create a new folder. You are asking the operating system to do that for you, and it will write a new folder to the disk. If you want to print a file, you say, all right, I've finished my document for today or whatever, file print. What that's saying is, right, operating system, please find the data that's associated with this picture on the screen that I can see. Find the data, in other words, the content of the document, and then send it to the printer. Now you might remember when we used to have to install device drivers. Whenever you put in a new piece of hardware and you have to install a device driver, or Windows these days is a lot easier to use than it used to be, and it comes with a lot of device drivers built in. What a device driver is when the operating system tries to write to the printer, each printer works differently. So if you've got an Epson printer, Windows would need to know it's an Epson printer, and it would need to execute the code associated with that particular printer. If you change it for a Hewlett-Packard printer, then you would need a Hewlett-Packard device driver, in other words a piece of software that converts the text that you're trying to print into data that the printer understands. And so the device drivers are installed within Windows. These days Windows comes with most device drivers, so if you are a printer manufacturer, you'd write your own device driver code and make sure you send it to Microsoft and say add this into the next Windows update. So when Windows says it's been updated, it's being updated with all sorts of stuff. It could be security patches, but it could be that some other people have created new device drivers, or they've updated device drivers and they're being rolled into the operating system. All sorts of stuff gets rolled in when you update Windows. So any interaction between your application and the hardware, or the hardware and your application, is controlled by the operating system. It's basically a broker between the hardware and the software. Okay, so the key terms or the key takeaways from this are: software consists mainly of computer programs and data. The program is the execution of a precisely written set of logical instructions. In other words, we need to follow the syntax of the particular language, and the logic has to be correct. Flowchart is a graphical representation of the sequence of logical steps, rather than it being just a written down sequence. Application software just programs and data which perform tasks on behalf of the user. A subset of that is web software, is specifically written to run on the internet, so you tend to have the user interface in a web browser, and then the back end website, sort of Tesco or Amazon or whatever, will be on the cloud or in their data center. Mobile applications are written specifically on a mobile device. They need to be written a bit differently than desktop because phones are not as powerful. Plus, you need to write the code quite efficiently, because obviously the more processing that's being done, the quicker it runs your battery down. System software though is different. This is more of a broker between the application and software and hardware. So application software and hardware. So this is running in the background and doing a lot of housekeeping for you. So requests from your software to the hardware will be implemented by the operating system. Any hardware events that happen, such as a key press or a mouse move or whatever, that go through the operating system, and then the operating system will direct those events into your software. Software or programs, executable code is loaded from long-term storage, such as a disk, into RAM. The operating system will do that. So typically you might double click something that's got a .exe extension, the operating system will load that into RAM, and then the CPU will start to execute it. An algorithm, just a step-by-step set of instructions, quite a generic description of the task that you're trying to implement. Pseudocode is less generic, it's a bit more detailed, but still written in just a written language. So it's not a program language specific. So you could write the pseudocode and decide which programming language you're going to use afterwards. Source code is the implementation of software in a human readable programming language, such as C, C++, C#, JavaScript, Java, Python, the things we looked at, and there are plenty more. Too many really. I think a lot of it's reinventing the wheel, but again, that's my personal opinion. So that's readable. Machine code is the equivalent of source code, but in a machine executable programming language, and so if you're using an interpreter, that's going to translate source code into machine code, but it's going to do it a line at a time. And so when you distribute your code, you've got to distribute the source code, which you're giving away all your secrets. If, however, you're using compiled language, then the compiler will convert the whole file of source code into a file of machine code. It's that machine code that gets distributed. So, for example, Microsoft are giving no secrets away when you install Office, because they've only provided executable files, which, as you've seen, they're not particularly readable. And so the operating system is a system software acting as a broker between application software and the hardware. Okay, I hope that's been of value, and we'll do another one.